Hello everyone, today we will be talking about the magic of Taylor series, approximating the impossible. Have you ever looked at a wild function like sin x, e to the x, or ln x and thought, how do calculators even compute this? Well, it turns out they don't use the actual function. They use Taylor series, a way of building an infinite polynomial that acts just like the real thing near a certain point. Today, we'll break down what a Taylor series is, how it works, and why it's so mind-blowingly useful. Let's start simple. When you zoom in close to a smooth curve, it starts to look straight. That's the idea between linear approximation. We use the tangent line to estimate the function nearby. But a straight line only captures the slope. What if we want more detail, like how the function bends or twists? That's where Taylor series comes in. The idea is to build a polynomial that mimics the original function at one point, not just its height, but its slope, or first derivative, its curvature, second derivative, its twist, the third derivative, and so on. It's like creating a mathematical body double, using derivatives as ingredients. Let's say we want to build a really good approximation of cosine x near x equals 0 using just a simple quadratic, something like p of x equals c0 plus c1x plus c2x squared. Our goal is to figure out what these constants are, c0, c1, and c2 should be so that this polynomial behaves like cosine near 0. First, think about what cosine x actually equals at 0. Well, cosine of 0 equals 1. That means if our approximation is going to be any good at all, it should also equal 1 when x equals 0. If you plug 0 into this polynomial, all the x terms disappear and you're just left with c0, so we'll set c0 equal to 1. Next, let's think about the slope. That is, how steep is the cosine curve at 0? The derivative of cosine x is negative sine x, and sine of 0 is just 0. So the slope is flat, horizontal at x equals 0. Now, let's take the derivative of our polynomial. P prime of x equals c1 plus 2c2x. Plug in x equals 0 and we get p prime 0 equals c1. So to match the flat slope of cosine at 0, we set c1 equals to 0. Finally, let's capture how the curve bends. This is where the second derivative comes in. The second derivative of cosine x is negative cosine x, and at x equals 0, that equals negative 1. That means cosine is curving downward at this point. Let's compute the second derivative of our polynomial. P prime of x equals 2c2. So to match the curvature, we set 2c2 equal negative 1, which becomes c2 equals negative 1/2. Putting it all together, we get p of x equals 1 minus 1/2 x squared. This is our quadratic approximation of cosine x near 0. It wasn't a guess, it was built systematically to match the function's value, slope, and curvature at a single point. And it turns out it's actually a very good approximation for small values of x. The general rule becomes f of x is approximately equal to f of 0 plus f prime of 0 x plus f prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed, and so on. Each term is the nth derivative at 0, divided by n factorial times x to the n. That division is crucial. It keeps the match precise. So all these factorials, and it starts to get confusing. Well, let's go back to our cosine example. We originally had p of x equals 1 minus 1/2 x squared. The third polynomial was sine of 0, which just equals 0. But now we take the fourth derivative of our polynomial, and what do we get? Well, when you keep applying the power rule over and over with those exponents all hopping down in front, you end up with 1 times 2 times 3 times 4 times c4, which is 24 times c4. So if we want this to match the fourth derivative of cosine x, which is 1, c4 has to become 1 over 24. Want to see something super cool? Let's try e to the x. The derivative of e to the x is e to the x, every time. And at x equals 0, it's 1, so every term becomes 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. That's the Taylor series for e to the x, and it converges everywhere. Add a few terms and you get a surprisingly accurate result. That's how your calculator estimates e squared. It just adds a bunch of polynomial terms. If it was not already apparent, why are these Taylor series so important? Well, they take all the local behavior at one point, how the function bends, twists, stretches, and uses it to rebuild the function nearby. Each derivative you add improves the match, and since polynomials are easier to work with than functions like sine or exponential, this lets you solve problems that were way too hard before. But it's not always perfect. Sometimes the approximation only works close to the point you're centered at. For example, the Taylor series for ln x centered at 1 only works between 0 and 2. Past that, it falls apart. Or, in other words, it diverges. That limit is called the radius of convergence, which we can talk about another time. So, in essence, a Taylor series is really just rebuilding a function nearby using just polynomials. It's one of the most elegant and practical tools in all of calculus. So, the next time someone says math can't be creative, show them a Taylor series. It's function mimicry, powered by derivatives, and that's kind of beautiful.